what we get is this thing cancels out. We get partial squared psi over partial x squared is equal to negative 2m over h bar squared times e psi. Actually, let me put this e with the 2me. So we make it like that. No. What is it? Negative 2me over h bar squared times psi. And now I'm going to do this neat little trick. I'm going to say, what I'm going to do is that I'm going to say that k, let's just call this thing k, it's a dummy variable, it's a constant variable. It's going to be equal to square root of 2me over h bar, which is the same thing as saying it's equal to the square root of 2me over h bar squared. Well, we're going to use this. So this variable k is going to soak up all the constants, because e is a constant, m is a constant, h bar is a constant. These are all constants. So it's going to soak up all the constants, and what we get if we plug that back in, let's see, what do we get? So 2me, if we square that, we get 2me over h bar squared, right? So what we get in the end is del squared psi over partial x squared is equal to negative k squared psi. And we've seen this before. Well, you should have seen this before. It's the equation for the simple harmonic oscillator. Simple harmonic oscillator. And there's already a solution for this that we already had. The solution for it is that psi of x is equal to a constant times sine of kx plus b, another constant, times cosine of kx. Okay, not too hard. We just solve this second order partial differential equation. And now we want to find essentially a and b. And then we're done. We've solved for the stationary states, and we can make a generalized wave function based on these stationary states. But the problem is solving for this a and b. Okay, so I have just made some more room so we can solve this. So we just said that psi of x is equal to a sine of kx plus b cosine of kx. Okay, now remember when we drew this picture, this picture for the infinite square well, we said potential well, we said it was 0 here from 0 to a, and then infinite anywhere else. I should be drawing this in a different color. So 0 here and infinite anywhere else. And we said, so that this implies that at the boundary, that means at 0 and at a, we have that psi of 0 is equal to 0 right here, and over here we have psi of a is equal to 0. These are called our boundary conditions. And from these boundary conditions, we can solve for a and b. How, you might ask? Let me show you. So we have psi of 0. Psi, let me just write a little better. Psi of 0. And this is equal to a sine of 0 plus b cosine of 0. What's sine of 0? This thing just turns out to be 0, so this whole thing gets out of here. And now psi of 0 is just b cosine of 0. What's cosine of 0 is just 1, so this is equal to b. And we said that psi of 0 is equal to 0, so this means that b is equal to 0. So we're plugging in our initial boundary conditions to our wave function that we've just got, and then we're solving for these constant a and b. and we found that b is equal to 0. So now we have, a nice and improved wave function, which is now just a sine of kx. But now we have to solve for a, and we've already used this boundary condition, so what's left? G, I don't know, maybe this one. Okay, so let's just plug it in. Psi of a is equal to a sine of ka. Nothing is canceling out here, so what do? We just use this little trick we have here. This is equal to 0, remember? We don't care about this a right now. Forget it. We want to know when sine of ka is equal to 0. And if you studied trig before, then you would know that sine of anything is equal to 0. Let's just see. So sine of 0, let me just write this as a theta, an angle, degrees. So sine of 0 gave you 0. What else gave you 0? Not 90, that gave you 1. So sine of, what else? Pi gave you 0. What else? Sine of 2 pi gave you 0. What else? Sine of 3 pi gave you 0. So if we have an axis, everywhere on the x is always 0. 0, 0. So f of 0 is 0. And then same thing here. So this is 0, pi, and then any multiples of pi. So we have n pi multiples. So if n equals 1, then we just get pi. If n equals 2, we get 2 pi. If n equals 3, we get 3 pi, and so on and so forth. So that's what we got, and then we could substitute this back in. So we want n pi is equal to ka, because sine of n pi is equal to 0. Let me just write that. It's very important to solving this. So sine of n pi is equal to 0, as we just found out. So that means, and we want to find when sine of ka is equal to 0. So n pi has to equal ka. We solve for ka. I mean, not solve for ka. We just solve for k. K is equal to n pi over a. And then n, of course, is equal to 1, 2, 3, dot, dot, dot. And this is relatively important. Why? Because what is k? Let's rewind back to when we've made k. So we said that k was our dummy variable consisting of all the constants we have. So we said k was equal to 2me over h bar. Now watch this. Let's just solve for E, the energy of the system. E is the energy. Let's multiply by h bar on both sides. Watch closely. Kh bar is equal to square root of 2me. Let's square both sides. K squared h bar squared is equal to 2me. Divide by both sides, we get E is equal to k squared h bar squared over 2m. Now let's just rewrite that. E is equal to k squared h bar squared over 2m. Now we said the k was a function, it had n in it. So, and n is an integer, so we could just write k sub n, depending on what n is. Now let's just substitute it back. E is equal to n squared pi squared, n squared pi squared over a squared. And we have this h bar squared over here over 2m a squared, e sub n. Now this is very important. What this is saying is that energy is quantized. You know, in classical mechanics, you just had any energy. You could pick an energy. It doesn't matter what the energy is. But look here. Energy is quantized based on this n. So that means we can't just have a regular energy. Our energy is going to be quantized in the order of pi squared h bar squared over 2m a squared. So we can have an energy of this, and an energy of this, an energy of this, an energy of this, and so on. But it can't just be some regular crazy energy that varies like that with time. What is this? No, it's quantized. Energy versus position. Energy versus whatever. That's not the point. What I'm saying is that energy is quantized, and that's the fundamental purpose of quantum mechanics. Why do you think it's called quantum? Quantum mechanics, all energy and all wave functions are quantized. It's very important. What else can we get from this though? If we want to normalize this wave function, we're going to do normalization of a squared, which is our normalization constant, times sine squared of kx, because we had that kx over here, remember? And then dx. And then if you do that integration from 0 to a, because we're only worried about when the wave function is from what we can actually solve, so then that's going to be equal to 1, which we know from our normalization conditions, which is a squared times a over 2, and then we get that a is equal to square root 2 over a. That's not really important. That's just our normalization function. Not function, normalization constant. Okay, so let me just write up here. Now we can get our stationary state wave functions, psi n of x, which depend on n, which is just an integer. So that will be equal to square root of 2 over a, which we just found is our normalization constant, times what we found for our actual wave function, sine of n pi x over a. And now I'm just substituting k with n pi over a, because we just found that somewhere here, right here. Okay? And that's our stationary wave functions for the infinite potential well. Stationary wave functions. And you can see here that the wave functions are also quantized because it's on n. It's not just any wave function, it's quantized. And we said, I didn't mention it before, but it was also important because before I didn't allude to it because I was going to say it now. Before we also had this sub-index of n, so that meant from the get-go that it was quantized. And from this we can make our, let me just make some room here. Anyways, from this we can make our actual generalized wave functions without the indices. So it will be capital psi of x and t, and that will be the sum from n equals 1 to infinity of a constant of our constants, or sum of our constants, c sub n, times psi of n of x times e to the negative I et over h bar. Let's just substitute it back in. We get that psi of x and t is going to be the sum from 1 to infinity of c sub n, and what is this? Is just radical 2 over a sine of n pi x over a times e to the negative I et over h bar. Let's clean this up a little bit. So psi of x and t is equal to, we can pull out the radical 2a because it's just a constant out of the sum. So we get the sum from 1 to infinity of sine of n pi x over a times e to the negative I et over h bar. And this is our